Today we're going to get very specific and talk about the sampling distribution of p-hat, or the sample proportion. And this is a lot like what we looked at with the chips example, because we were taking the proportion of red chips. So out of my 200, I took samples, 500, actually I think this is 505 samples of 40 red chips and calculated the proportion of those that were red. So each of those proportions, each one of these dots right here, is a value of p-hat. Now this is not a sampling distribution, remember, because I didn't take every possible sample, but this is the beginnings of a sampling distribution. So today we're going to talk about those specific distributions, those specific sampling distributions that work with p-hats, and how we can figure out the things like the mean and the standard deviation of those sampling distributions. So here, whenever we're looking at the sampling distribution of p-hat, we will have some that are approximately normal. Okay, we're pretty much not going to have any that are perfectly normal, so whenever you talk about normal, you always want to make sure you say the word approximately. This is very, very important to say approximately normal and not just normal. But some of them will be approximately normal, and which helps us out because whenever they're approximately normal, we know how to handle those. We draw a picture, do a z-score, and look at table A. And that will tell us everything that we need to know. So it's important to know when we can say that they're approximately normal. And we can say that it's approximately normal as long as n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. As long as both of these are true, we can say that it's approximately normal. And when it's approximately normal, that means we can draw pictures, do our z-scores, and do table A to find out the proportions of values less than, which would be like the probability of getting a sample proportion less than 10, or 0.1. Okay, so what is the mean and standard deviation of the sampling distribution of a sampling proportion? So if I have something like this chips here, and I know that it's a sampling distribution, how can I go about finding the mean and the standard deviation of this? Okay, well, if I know the population parameter for proportion, p, that is what the mean is. So if I know the proportion, I can use it to find the mean, because the population proportion is the mean of the sampling distribution. And you can see that here. Even though it's not a sampling distribution, our mean would be 0.5, which is the actual proportion of red chips in my population. Okay, so whatever your true population proportion is, that is the mean of your sampling distribution for p-hat. Okay, the standard deviation for p-hat is the square root of p times 1 minus p divided by n. Okay, however, this is only true if n is less than or equal to 1/10 of the population, which is also written as 10 times the n sample size has to be less than or equal to the population size. This is the one that we've been using, but the actual one says this, but they are the same thing. Remember, we call this the 10% condition. And the reason this is important is because of independence. Remember, in the last chapter, we had to check the 10% condition anytime that our scenario wasn't going to be independent. Well, because we're talking about sampling and proportions of things when I sample, they're never going to be independent situations. Because every time I pull something out of my sample, that changes the probabilities of everything else getting picked. So always, 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 I have to check this. Always. No ifs, ands, or buts. Always, always, always. I have to check this. Okay, so you might say, all right, well, what does this do for me if I'm never going to actually know the population proportions? Okay, which is true. In real life, we usually don't know these. But in real life, we're not usually trying to find the value for the sampling distribution. In real life, we are usually taking the mean of several p-hats and we're going to use that to estimate this. So it still is very useful because I know that I could go either way with this. If I have information about the sampling distribution, I can use it to estimate a value for the actual parameter. Okay, so let's look at the check your understanding questions on page 437. Check your understanding and then compare your answers to mine. The first one is looking for the mean of p-hat, which we can see is 0.75. The second one is telling us the standard deviation of p-hat, which is 0.0137 when I calculate that. The third one, I say n times p. That's 1,000 times 0.75, which is 750. And I have to say n times 1 minus p. That's 1,000 times 0.25, which is 250. So both are greater than or equal to 10. So, yes, they are approximately normal. Okay, and 4, it would still be approximately normal with a p-hat equal to 0.75 and our standard deviation would be the square root of 0.75 times 0.25 over 9,000, which is 0.0046. And it's important to note here whenever I do the standard deviation that I can assume there are more than 90,000 young adult internet users. Okay, there's a couple of things to note here, and the reason I have to assume this is because I have to talk about the 10% condition in order for me to assume it's independent and be able to use my standard deviation. So again, always remember the 10% condition. Something else that you want to do is right here, say 9,000 times 10 so that they can see where this 90,000 is coming from. And whenever they ask you to talk about whether or not something can be considered normal, sampling distribution of p-hat can be considered normal, show your work. Always, 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 if there is work to show, please show it in order to make sure that you get full credit. I cannot stress that enough. Okay, so if you have something where your answer does not match mine and you can't understand why, make sure that you come and talk to either Ms. Truax or myself. Okay, one of the big things in this section is what do we do when this sampling distribution is normal? How does that help us solve problems? And so I've got two examples here where we are going to use the sampling distribution to solve some probability problems. Okay, so the superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a four-year college or university. Suppose that 80% of all middle school students in her district are planning to attend a four-year college or university. Okay, if she's wanting to know about the proportion of middle school students in her district, and it tells us this right here, that makes this P. Because that's giving me the true proportion. Okay, so what is the probability that a SRS of size 125, there's my N, will give a result within 7 percentage points of the true value? So basically I'm asking about a p-hat. What is the probability that my p-hat is going to be within 7 percentage points, which means it's going to be less than or equal to 0.87, but greater than or equal to 0.73. Because when I subtract 0.07, 7 percentage points, from 0.8, I get this, and when I add it, I get that. So this is my question. What is the probability that it's going to be between this? Okay, so I want to state, what is the probability that the percentage of sampled middle school students who have plan to attend a 4-year college or university falls between 73% and 87%. So there's our state. Next, we want to plan. And when we plan, we need a couple things. First things first, let's write down what we know. I know that if I'm talking about the probability that I'm going to get a sample proportion, okay, the probability of p hat, that means I'm dealing with the sampling distribution. So when I see something like this, what is the probability that a simple random sample will give a result? Things like that tell me that I'm dealing with the sampling distribution of p hat. And I know that the mean is equal to the true proportion, which is 0.8. Okay, then I want to say, is this independent? Can I say that this is independent? So I want to check my 10 times my sample size. Well, 10 times my sample size is going to be 10 times 125. So that's 1,250 students. Because the district is large, we can assume that our population, capital N, is greater than or equal to 1,250. The standard deviation would be P times 1 minus P divided by N. So that is 0.8 times 0.2 divided by 125. Then you take the square root, and we get a standard deviation of 0.036. So the question is now, what do we do with all this? Well, hopefully the information that we have tells us that this is normal. Because if it's normal, like I said, we know what to do with it. If it's not normal, then we have some problems. So let's check to see if it's normal. That's always what we want to do. Our sample size is 125. So N times P, that's going to give me 100, which is definitely greater than or equal to 10. And 125 times 0.2, that gives me 25, which is still greater than or equal to 10. Since both of these are greater than or equal to 10, therefore, we can assume the sampling distribution of p hat is approximately normal. Well, I have everything I need. If I know that I can consider it normal, and I have a mean, and I have a standard deviation, then from there on, it's pretty simple. I draw my picture. My mean right here in the middle is 0.8. I wanted to know what's the probability that it's going to be between 0.73 and 0.87. So I'm looking here in the middle. Okay, which means I'm going to need two z-scores because I'm going to need one for 0.73 and one for 0.87. So I say z equals 0.73. It's always actual minus the mean divided by my standard deviation, which is 0.036. And over here I say z equals 0.87 minus 0.8 divided by 0.036. And notice that these are actually going to be the same z-score, but this one will be negative and this one will be positive. And you don't even actually, if you're doing this and you're using the calculator, don't even actually have to write the z-score down. If you just have the formula, that is good enough. Because the calculator, using normal CDF, would do this for you. There's a way to have it do it for you. If you don't want to actually calculate the z-scores all the way through, you can do normal CDF. Now, if you're using table A, you got to do the z-scores because there's no other way. But if you're doing normal CDF, which is easy too, because then I can just put these two down. My lower value would be 0.73. My upper value could be 0.87. Then instead of putting 0 and 1, I put my actual mean, which is 0.8, and standard deviation. This will give me my actual value, which tells me that the probability that p hat is going to be between 0.73 and 0.87 is 0.948. Okay, so you could do it either way. I can use table A, but in table A I have to find the things to the left of both of these and subtract, and I have to actually calculate out the z-score. If I choose to do normal CDF, that's fine. I can do it all in one step. However, I still have to show all of this work in order to get credit. And not only do I have to show all of this work, I also have to have a conclusion. My conclusion would be about 95% of all simple random samples of size 125 will give a sample proportion within 7 percentage points of the true population proportion. There's my conclusion. Okay, let's talk about what this means. What this means is that what I've proven here with all of my math is about 95% of any sample, of all the samples I take. So, will be within 7 points. So, basically, I have a 95% confidence that when I take a sample, it will be within 7 percentage points because about 95% of all samples should lie within those 7 percentage points. Okay, let's look at one more example, just in case that one wasn't clear enough. Maybe this one will help. Harley-Davidson motorcycles make up 14% of all the motorcycles registered in the United States. So you plan to interview a simple random sample of 500 motorcycle owners. How likely is your sample to contain 20% or more of people who own Harleys? So I want to state, what is the probability that the proportion of motorcycle owners in my sample who own Harleys is 20% or more. Okay, if I were to write this in symbols, really what that means is what is the probability that p hat, which is my sample proportion, is going to be greater than or equal to 0.2. Okay, so once I state I have to plan, let's write down everything we know. I know since I'm asking, how likely is it that my sample does something? If I'm talking about the probability of my sample, that means out of all possible samples, how many times should this occur? Because remember, probability is just long-term relative frequency. So what's the proportion of times that this should happen out of all of the samples? So I need the mean of my sampling distribution, which I know is going to be close to the actual value, so 0.14. I need my standard deviation. So that would be the square root of 0.14 times 0.86 divided by my sample size, which is 500. And I am going to get the value of 0.0155. And I need to make sure that I mention we can assume there are more than 10 times 500, which is 5,000, motorcycle riders in the U.S. Okay, it's important that I say that, remember, so that I can use my standard deviation. Okay, I have a mean, I have a standard deviation. I don't know what I'm going to do with those unless it is normal, so let's check normality. 500 times 0.14, that's 70, which is greater than or equal to 10. And 500 times 0.86 is 430, which is also greater than or equal to 10. So we can assume the sampling distribution, and I'm going to abbreviate because I'm running out of room, of p hat is approximately normal. Okay, so there's my plan. I have my mean, I have my standard deviation. I'm showing that it's normal, and I'm showing that I can use the standard deviation because it's independent. And so now, what am I going to do with that? Well, since it's normal, let's treat it as it's normal. My mean here, I know is 0.14. I'm wanting to know what's the probability that I'm going to get a sample that has 0.2 or more. So out of all of the possible p-hats I could get, because remember, this is full of p-hats. Everything in here is a p-hat. So there are p-hats, you know. The very peak of it, that line is 0.14 because that's the mean. But every piece of data in this distribution, even though I'm drawing it as a density curve and not as a dot plot, everything in here is a p-hat. So basically I'm saying how many p-hats are there that are 0.2 or above, because out of all of the possible ones, those are the ones I'm interested in. So what's the probability that I'm going to get one that fits that description? So I find a z-score, because that's going to help me out. Z is equal to 0.2 minus 0.14 over 0.0155. And again, I can calculate it, and I will this time just so you can see it. 3.87. Okay, this is really high. Telling me that this is really high means my probability is going to be really small, because if I know that this is normal, I know that 3 standard deviations covers 99.7%. Since this is above 3 standard deviations, that means that there's at the very, very most like 0.15 of a percent, so 0.0015 at the very most, because there's only 0.3 of a percent left, and half of it would be on the bottom half. So this is going to be a very, very, very small number. If you look in Table A, it's probably not even in there, which means you're going to say something to the effect of my p-hat, the probability that my p-hat is greater than or equal to 0.2, and you can use these squiggly lines, which mean approximately, and it's approximately 0. Because this is so close to 0, we're going to say approximately 0. And I can do normal CDF with this, and it will give me a value, but it's going to be a very, 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 very small value. So why not just approximate it and say 0? So we still need to conclude. And what we're going to say in our conclusion is, it is extremely unlikely we would get a sample of 500 motorcycle riders in which at least 20% own Harleys. Okay, so there's two examples of using the normal approximation of p hat. So remember the formulas for the mean and the standard deviation for p hat. And remember that those formulas, or know that those formulas are given to you on the AP formula sheet. You got to know how to use them and got to know which ones they are, but they are written on the formula sheet, and know how to use the approximation for the normal distribution for p hat.